What's up, biology students? Mr. Holloway here. In today's video, we're going to talk about atoms, molecules, and atomic bonding. In order for us to understand how living organisms function, we need to understand a little bit about biochemistry. And to understand that chemistry, we need to understand these things called atoms, the building blocks of matter. Atoms are small. You won't believe just how tiny, itty-bitty, mind-bogglingly small they are. I mean, you may think that a grain of rice is small, but that's just peanuts to atoms. Listen, take the tip of your pencil, for example. The stuff that we call lead is actually graphite, and graphite is pure carbon, meaning it's made out of nothing but carbon atoms. Let's say this tip of your pencil, if it were to break off, has a mass of about 1 gram all on its own. That 1 gram of graphite contains over 50 sextillion atoms. That's over 50 billion sets of 1 trillion atoms each. That's a lot of atoms, and remember, that's only the tip of your pencil. Carbon is a really important atom to know about from a biology point of view, but there are a lot of other kinds of atoms too. Here we see the periodic table of elements. This table lists all the known elements in the universe organized according to their composition and their chemical properties. An element is a pure substance made up of only one kind of atom, so you can think of the periodic table as a kind of list of all the different types of atoms that we know about. Matter is made of atoms, but atoms are also made of smaller things. We call these smaller things subatomic particles, and there are 3 of them: positively charged protons, neutral or non-charged neutrons, and negatively charged electrons. Protons and neutrons are found in the nucleus, or center of an atom, and make up almost all of the atom's mass. Electrons have almost no mass, even by comparison to something as small and as light as a proton, and they have a negative electrical charge. Electrons are found outside the nucleus of the atom, in a cloud that surrounds the nucleus. This cloud contains different orbitals, or energy levels, and electrons move around inside of these energy levels at nearly the speed of light. All atoms are made of these 3 subatomic particles, just in different quantities, and the periodic table of elements can tell us a lot about how many protons, neutrons, and electrons a particular kind of atom contains. The main difference between atoms comes from how many protons they have in the nucleus. This is kind of the defining feature of an atom. And as we read the periodic table from left to right and top to bottom, the number of protons in the nucleus of those atoms increases. Let's start by looking at hydrogen, the first element on the periodic table. Hydrogen contains only 1 proton in the nucleus and 1 electron in the electron cloud that surrounds the nucleus. And that's why the atomic number for hydrogen is 1. For any element, the atomic number always refers to the number of protons that atom has in its nucleus. The atomic symbol for hydrogen is H, and we often use the atomic symbol as an abbreviation for this kind of atom. For example, water is called H2O, H2 for 2 atoms of hydrogen, and O for 1 atom of oxygen. The atomic mass of an atom is determined by how many protons and neutrons the average atom of this kind contains, because both protons and neutrons contribute to an atom's mass, while electrons do not really. The atomic mass of hydrogen is slightly more than 1, because this number is an average mass, and while the vast majority of hydrogen atoms contain 1 proton and 0 neutrons, some hydrogen atoms contain 1 proton and 1 neutron, and a rare few contain 1 proton and 2 neutrons. These different forms of hydrogen are called isotopes. They all have the same number of protons in the nucleus, 1. That's what makes them hydrogen. But they all have different numbers of neutrons. The mass of this first and most common isotope of hydrogen is 1 atomic mass unit. The mass of this second, less common isotope is 2 atomic mass units, and the mass of this third and very rare isotope of hydrogen is 3 atomic mass units. In all cases, the mass is the same as the number of particles in the nucleus. This last one also happens to be radioactive. It's unstable due to how many extra neutrons there are crammed into the nucleus. Let's do another example, this time with carbon, which is the single most important element for living things. Carbon has an atomic number of 6, meaning it always contains 6 protons in the nucleus. It also has an atomic mass of 12.01 AMUs, which is the average mass of a carbon atom based on how many protons and neutrons it contains. 12.01 is about 12, meaning that 12 is the number of protons plus neutrons in the nucleus of a carbon atom. Since we know that there are 6 protons, there must also be 6 neutrons in the average atom of carbon. Here we can see some of the isotopes, or different forms of carbon. The vast majority of carbon atoms have 6 protons and 6 neutrons, and we call these kinds of carbon atoms carbon-12. But a small percentage of carbon atoms have 6 protons and 7 neutrons, so we call them carbon-13. And some even have 6 protons and 8 neutrons and are called carbon-14. This last one, carbon-14, is radioactive and is the isotope used in carbon dating. In this diagram, we can also see those different electron energy levels I talked about earlier. Electrons start by filling in the lower energy levels, and once that level is full, they start filling in the higher energy levels. The first energy level can only hold 2 electrons, which is why all of these isotopes only have 2 electrons in this inner circle. The second and third energy levels can each hold up to 8 electrons. Since carbon has 6 protons, or 6 positively charged particles in the nucleus, a neutral atom of carbon will also have 6 negatively charged electrons to balance them out. 2 of these electrons will fill in the first and lowest energy level, and the remaining 4 electrons occupy the second energy level, as you can see here in this diagram. If you're wondering why this business of electrons and energy levels is important, it's because electrons, especially the outermost electrons, have everything to do with how atoms form bonds with one another to form bigger, more complex structures. One way that atoms can do this is through covalent bonding, which is when atoms essentially share the electrons they have in their outer or valence shell. Water molecules, for example, form when an oxygen atom shares electrons with a pair of hydrogen atoms. This is why we often refer to water as H2O, H2 for the 2 atoms of hydrogen and O for the 1 atom of oxygen. By sharing electrons, all these atoms are able to fill up their outer or valence shell. Each of these hydrogen atoms kinda has 2 electrons now, and 2 electrons is all this first energy level can hold. Meanwhile, this oxygen atom kinda has 10 electrons now, 2 in the first energy level, which, like I said, is all that energy level can hold, and 8 in the second energy level, which is all that level can hold. By sharing these electrons, these hydrogen and oxygen atoms form a bond that is difficult to break and form a new substance that we call water. Here are a few more examples of simple molecules formed by covalent bonds, including hydrogen gas, or H2, for 2 hydrogen atoms bonded together, oxygen gas, or O2, for 2 oxygen atoms bonded together, water, or H2O, which we literally just learned about, and methane, or CH4, for 1 carbon atom and 4 hydrogen atoms. Most of these are what we call single covalent bonds, because each atom involved contributes a single electron to a shared pair of electrons. But this one here, between the 2 oxygen atoms, is actually a double covalent bond, because each oxygen atom contributes 2 electrons, and together these 2 atoms share 2 pairs of electrons. As you might imagine, a double bond is stronger and more difficult to break than a single bond. You might also notice that this carbon atom here is able to form a total of 4 single covalent bonds. That's pretty special, and this is what allows carbon to form the large, complex molecules necessary for life. But that's not the only way that atomic bonds can form. Atomic bonds can also form when electrons are transferred between atoms instead of shared. We call these ionic bonds because when an atom gains or loses an electron and takes on an electric charge, we call that atom an ion. Here's an example. Sodium, symbol Na, has only one electron in its outer shell, and one electron is pretty easy to lose. And if sodium can lose this electron, then it will have a full outer shell because this one already has 8 electrons in it. Along comes chlorine, and chlorine has 7 electrons in its outer shell. But if this chlorine atom picks up that one electron that sodium wants to lose, its outer or valence shell will be full too. So sodium loses 1 electron, and chlorine gains 1 electron. And both are now happy because each has a full outer shell of electrons. But now these two atoms are both electrically charged. Since sodium lost 1 negatively charged electron, that means it has 11 protons and only 10 electrons for an overall charge of +1. Chlorine has 17 protons and 18 electrons since it gained an extra electron, and thus has a charge of -1. Just like opposite poles on a magnet, things with opposite electrical charges are attracted to one another. So the positively charged sodium ion is attracted to the negatively charged chlorine ion, and this attraction is what causes these ions to stick together in an ionic bond. We don't call these ionic compounds molecules, but they are still capable of forming large, complex structures. Table salt, or sodium chloride, is formed in this manner, and if we were to zoom way in on a single crystal of salt, we would find an alternating lattice pattern of positively charged sodium atoms and negatively charged chlorine atoms, as depicted here in these figures. It's also interesting to note that sodium chloride behaves very differently than either sodium or chlorine do on their own. By themselves, sodium is an explosively reactive metal and chlorine is a poisonous toxic gas. But put these two together and you have a substance that is not only harmless and edible, but which is also necessary for life. And we wouldn't be able to survive without at least a little bit of sodium chloride in our diets. Water is the same way. Hydrogen by itself is explosive, and we certainly couldn't drink either liquid hydrogen or liquid oxygen. But put them together in a water molecule, and we have a substance that is perfectly harmless, and which is necessary for supporting life as we know it. Sometimes it works the other way too, and atoms that are harmless on their own turn out to be incredibly harmful when combined with other things, but that is a story for another day. So in summary, all matter is made of atoms, and all atoms are made of protons, neutrons, and electrons. The number of protons is what defines an atom, and its electrons allow it to bond with other atoms to form the molecules and compounds necessary for supporting and maintaining life on this planet. When atoms share electrons, that's called a covalent bond, and that's how molecules are formed. When atoms completely transfer electrons, gaining or losing them, they become electrically charged ions, and these ions stick together in ionic bonds, forming compounds like table salt and a great many other important substances. These ideas make up the basis of our understanding of matter and of chemistry. Life, as it turns out, is one giant chemistry experiment, and there are literally millions of chemical reactions occurring inside of you right now, controlling everything from digestion to emotions and even consciousness. Something to think about. And with that, I will bring our video to a close. Thanks for watching, everyone.